Thank you very much, Baruch. It's a real pleasure to be here. It's nice to be back in the United States, too. I spent the last 3 years at the International Institute for Applied Systems Analysis, working essentially on global change problems. And now I'm back at USC, going back to my profession, which is decision and risk analysis in particular. What I want to do in the next 20 minutes, I'd like to start off with a rather generic scheme of decision-making and focus on how one can and should link decision-making to scientific knowledge. Then I will give 3 examples, one personal one, for my family actually. I asked for permission yesterday, both my daughter and my wife, to use this example. One technology choice, Department of Energy, and one public policy choice, and end with some conclusions about how one can better link science to decision-making. So basically this scheme that I start with is pretty uncontroversial, even though the term rationality is sometimes criticized or looked at with suspicion. But it's always true that decisions depend on what one believes and what one values. And I put this X in the middle, that's evocative, but it really also in some cases means multiplication. If you interpret beliefs as probabilities and values as utilities, what you got is a probability times utility or expected utility model, which is kind of the standard prescriptive model in decision making. But this kind of simple model is also true about most descriptive work, whether that is prospect theory or generalized utility theories. So it's a pretty general framework. Now, science comes in one very important way in this framework, and that is by educating and helping forming beliefs about facts, about uncertainties, et cetera, et cetera. I put a question mark into the box that links science to values, because that is not really the major input into decision making, but a little bit of science contributes to that as well. For example, if you're talking about research on the value of life or research on various other trade-offs. Unpacking this a little bit, beliefs have various facets. They could be facts or assumed facts. They could be opinions, expert judgments, and usually they're surrounded with significant uncertainties, and that is a particular part that decision makers have to deal with. On the value side, we're dealing with objectives. That is what we want to achieve, how to measure these objectives, and how to make trade-offs among them. And decision analysis, my discipline, puts all this together by helping people formalizing facts, opinions, and uncertainties, objectives, measures, and trade-offs, model them, and inform decision-making. And in many ways, the way I have applied decision analysis, both in my personal life and in my professional life, is as a communicator between the scientific community, the expert community, and the decision makers. In a way, translating scientific knowledge through this decision analysis lens to assist decision making. So now I want to give 3 examples of this. First one I call turning the baby. Decision maker was my wife, with a little bit of help from me. The second one is providing a new supply source for tritium in the United States. Decision maker was Hazel O'Leary. And the third one is how to deal with electromagnetic fields from power lines. The decision maker there was the California Utility Commissions. Starting with the baby. This was about 25 years and 5 months ago. You will soon know why I remember that very well. In December of, end of November, early December of 1986. The baby that my wife was carrying at the time in her 8th month was in a breech position. And so the question was, should the baby stay in the breech position or should, as her gynecologist recommended, should it be turned? And the gynecologist recommended that the baby be turned. And the way you do that is by external manipulation of the baby. See, that's a pretty tight space in there. And so you turn the baby back into the regular position with the head down, and then you're more likely to have a normal birth. So the question on the table was whether to turn the baby or not. And as I already said, the gynecologist suggested that. So my wife was a little bit queasy about this, but asked me to call the gynecologist and talk to her. What she didn't know is that I would talk to her about decision analysis. The gynecologist didn't know that either. But my first question to the gynecologist on the phone, I had this decision tree in front of me. The gynecologist didn't know it. Would there be any possible complications? And she said, well, not really. And I said, what is the worst that can happen? And she said, well, the baby could get strangulated on the umbilical cord. And I said, oh, that seems pretty bad. What's the chance of that? And she said, well, it happens very, very rarely. She wasn't really willing to pin down, so I penalized her by giving it a 5% for complications, which in reality is probably more like 1% or less. Then I got a little suspicious and I said, well, what's next? And she says, well, sometimes the baby rolls back. I said, how often does that happen? She said about a third of the time. I later on read that it's between 30 and 40% of the time. So I still gave that a 30% that it, 70% that it rolls. Sorry, she said that it rolls back is about 2/3 of the time, and I later found out that it's 60 to 70%. And so I gave that 30% to be okay, staying in position. And then finally, I said, well, what's the chances that my wife would have a cesarean anyway? Because the whole reason why you're turning the baby is to avoid a cesarean. And she looked at the record and she said, well, your wife is 34 years old. That's actually better than even chance. So I put that other note in that says a 60% of having a cesarean and 40% of being okay. Now, I knew what the answer would be, because the outcomes, no matter how you look at it, is if you don't turn the baby, you have a cesarean. If you do turn the baby, there's about 10 to 12% chance of having a normal birth. The other cases are either cesarean or an emergency operation in case the baby was strangulated on the umbilical cord. So this is the factual side of the story. So I just filled in that one box of our decision diagram. The value side is my wife's. You can imagine what the next question is. I went home and I said, I have one question for you. And then the problem is finished. How do you feel about a cesarean versus a normal birth? And she was struggling, and I said, throw in the emergency cesarean, the emergency operation that could happen too. So, well, I mean, clearly the cesarean and the normal birth are very close. She wasn't even sure completely in which rank order it was. And at that point, the answer was clear that in terms of her values, having a normal birth wasn't so outrageously more valuable than having a cesarean that it would turn the decision. Now, you can do all sorts of math on this problem and sensitivity analysis, as I did, and anyway it comes out not to turn the baby. So I told my wife that, and my wife said, I knew that already. And I said, well, I said, that is great, because as a decision analysis, it's wonderful that if there's a convergence between the analytical thinking and the emotional thinking. And so we both decided to call the doctor the next day and cancel the appointment to turn the baby, but I had to call. So I called the doctor and told her that we didn't turn the baby. The doctor was very upset. She thought I didn't trust her. This is an interesting reversal of the trust situation. But I convinced her that there were circumstances that made this a reasonable decision. And she remained my wife's gynecologist, and she scheduled the cesarean months later, and we had a beautiful daughter who's now 25 years old. The next problem is a little bit more technical. Tritium is a radioactive isotope that decays at 5.5% a year, and it's needed as an ingredient of nuclear weapons. And until 1988, tritium was produced in a power plant, a heavy water reactor at Savannah River on the upper left there. But in 1989, for safety and pollution reasons, that power plant was turned off by then President Bush, the older Bush. Alternatives were, among others, to build an accelerator, which is the lower left picture. If we didn't have tritium, tritium would decay, as you see on this curve, exponentially, and it would cross the amount of tritium we need for start 1 in 2005, this was a problem in 1996, and crossed the start 2 line in 2011, last year. So the question on the table is, how should we produce tritium? And some of the alternatives that were being analyzed were build a new heavy water reactor, build a gas-cooled reactor, or light water reactor, or a linear accelerator. There were in total 10 alternatives that were being considered, and there were about 100 people working on this for 2 years intensively, doing all sorts of studies. I was the lead decision analyst. I actually took leave of absence from the university and camped out in the DOE Forrestal building next to the Assistant Secretary of Defense Programs to help make this happen. And fast forward 2 years, late 1996, 97, we had everything on the table, and now we had to communicate this to Hazel O'Leary, who was the Secretary of Defense at the time. And we struggled mightily with taking 2 years' worth of work, analysis, cost analysis, production assurance analysis, environmental analysis, and put it into a simple communicating form, and this is what we came up with. This slide made the decision. So on the left, you see the alternatives. These are all the acronyms: HWR, heavy water reactor; MHTGR, the gas reactor; the light water reactors. There were 2 types of light water reactors, new ones and then commercially existing ones. So you can go into a commercial reactor and have tritium produced there. And the accelerator. And we analyzed production assurance, basically, can it be done on time? Can it be done with the capacity we need? And is it available? Cost, just total life cycle cost, and environment, mainly spent fuel and nuclear waste and some other environmental effects. For the heavy water reactors and the gas-cooled reactors, we concluded they had schedule problems. They couldn't do it in 2011, which was the date. So we said no-go independently of cost and environment, which weren't particularly attractive in those cases either. For the light water reactors, what you can see here that they have no problems producing tritium at all. The new ones cost a bit. We called it medium. We're talking here about $10 billion, so medium cost. And they produce spent fuel. The commercial ones also had no problems. It cost very little, like $1 billion to produce tritium in them, and they produce spent fuel. Well, you don't need to be a genius to figure out what to choose if you have a new build versus a commercial option. You go commercial. And finally, the accelerator kept on popping at the table. It was a very large project, also about $10 billion. We were somewhat twisted to call this a no problem for production assurance. Our analysis actually showed that there were some issues, but for a number of reasons, some of them political, we put on the slide no problems. We put on medium cost, although it was a little bit on the higher side, but we discounted. So when you discount, it turned out medium. And no waste was true. And that was really the selling point of the accelerator. It was the green solution. So I'm going to skip over the next few slides. Well, let me just give you one glimpse of this. And this is the cost analysis, a very elaborate cost analysis on trying to figure out what the uncertainties about the costs are. And here on the bottom, on the x-axis, we have all the different options, the 10 options. And then what you see here are box plots in terms of billions of discounted dollars. The boxes themselves are the uncertainty range from the 25th to the 50th percentile, so about 50% uncertainty that the actual costs are in there. This is the, I think this is the mean, and then this is the 5th to the 95th. So you see the cost uncertainties are very large, and you can't tell very much out of it, except that the 3 commercial options on the side are clearly the best ones in terms of cost. By the way, the engineering estimates of the costs are all at the lowest point of these graphs, the original engineering estimates prior to our risk analysis, and that tells you something about optimism built in an engineering cost analysis. So our risk analysis, which was quite elaborate, involved 20 cost experts, numerous elicitations, come up with this slide. Skip this one. In any case, based on the cost analysis, the environmental analysis, and the production assurance analysis, the decision was made to continue a dual path. So to go and create an office of commercial reactor production, so it was decided to go commercial, and to also continue the accelerator for a while. The primary source of tritium production would be decided on by the end of '98, and the construction would begin in 1999. And in fact, that is exactly what happened in 1999. Then Secretary Richardson decided to select down the commercial option. Smart move, my opinion. Of course, as an analyst, I don't say that. And shut down the accelerator production of tritium. And today, I don't know if today we really produce, but for several years since 2003, we produce tritium in the Watts Bar nuclear power plant in TVA. The last example is on electromagnetic fields. Some of you may know the problem. Epidemiological studies have linked EMF exposure to childhood cancer to leukemia since 1979. However, there has been no firmly established causal mechanism, and it's very hard to figure out what might be the case, although there is a suggestion that it's the magnetic component of the fields, and the highest fields are produced by high voltage power lines. Residents living near the lines worry about health effects and property values, and some regulatory action has been taken to reduce fields, for example, in California and in Florida. The key scientific issues are, is there a causal relationship between EMF exposure and health effects? What are the health endpoints and how strong is the link? And also, a somewhat scientific issue is there a reduction in property values due to the EMF issue? Here are some factual summaries. This is for consequences estimates per mile in 35 years for a 115 kV line in a populated area. EMF health effects in terms of life years, 6.8 life years lost. This is a huge model based on epidemiology and all sorts of assumptions. If you don't do any change, if you do a moderate, quite inexpensive change of rephasing the line, which is an engineering trick, you get this down by a factor of 5 roughly. Or if you're underground, you get it pretty much eliminate the health effects. The costs are very little for rephasing, little additional cost. For undergrounding, it's an additional 3 million per mile. Property values, you get a benefit, 1.6 million per mile. Then there were outages too, but that wasn't an important problem. Those are the facts. And don't take these numbers terribly seriously, because I show you how you can communicate this without actually being pinned down to these exact numbers. Now, the value side, the only numbers that weren't in dollars already were the life years saved and the outages. And there's literature on that. So in terms of life years saved, we used the literature and came up with 100,000 per life year saved. Life year, not life year saved. And about $1.10 in terms of productivity losses for an outage hour. Doesn't mean that people are unproductive during that hour, they just don't have electricity. Now, if you depend on the computer and the battery is gone, that's a problem. Here's the result. No change, rephasing, undergrounding, expressed in total equivalent cost. Now we have a metric because we have values involved. No change has a relatively high total equivalent cost of about 1.3 million. The blue part is the health part of that. Rephasing has a lower equivalent cost because the health part goes away and the actual cost stays the same. Undergrounding has the highest because of the cost of undergrounding is high, with some offset on property values. Nobody believed that. So we created this for the decision maker and anybody who wanted to know, and there were many people who wanted to know, where we took every single number in the model, put them on a slider, and gave it to people and say, you can play with every single number and can observe on the right how the bar charts change in terms of the relative total equivalent cost. So for example, if you put the probability up, then the blue part gets larger, et cetera, et cetera. The one thing that you can't do, or only under very extreme circumstances, is make this U shape go away. What does that tell you? It tells you that the detailed assumptions aren't that important, that rephasing is a pretty good idea and it is pretty cheap. And in fact, the California Public Utility Commission did have guidelines that for new lines required a small investment up to 4% of the total investment in order to reduce magnetic fields. So I think this sort of display, which looks prohibitive to the beginning, but once you play with it, it becomes very transparent and very useful, is something we do now frequently in decision analysis. So I got 2 more slides. Specific conclusions. It takes a special effort to link scientific knowledge to decision making. You can't just stand in front of a decision maker or an audience and say, here's everything I know about EMF, electromagnetic fields, and assume that they can make a decision on that basis. It takes an intermediary, and I think decision analysts, good decision analysts, can help in that regard. Values are often as important for decision making as scientific knowledge. Take, for example, turning the baby. It took both the scientific knowledge of the probabilities and the values of my wife to make the decision. It's very important to responsibly present uncertainties, like in the tritium example. Point estimates of the costs wouldn't have been particularly useful in that case. And transparency of decision models is very important. The ability of decision makers to actually play with them, test them, work with them, and figure out whether they make sense. And some general conclusions at the very end. Policymakers and ordinary people are usually trying to make rational decisions or reasonable decisions. I find very few people who are trying to obfuscate or cheat or to lie to me when I do a decision analysis. It happens. It happens sometimes when there are very deeply hidden political agendas, but most of the time the motives for decision making are to make the best decision possible. I believe strongly that science can and should inform this decision making process, and it takes analytical tools and communication skills to make that happen. It takes both the analysis part and the social part to make it happen. If you're just doing the analysis part, it can be a nerdy analysis and nobody believes you. If you just do the communication, you can come up with a dumb solution. To have both the science, the communication, and the analytical tools is very important. So with that, thank you very much.